Sometimes when you see a trig identity, it kind of feels like it's just handed down from on high and it just appears from out of nowhere, fully formed, and who knows what happened. And while mathematics is certainly magical, it is definitely not magic. Everything comes from somewhere. So this is the origin story, if you will, of the sum and difference identities. We're going to start with the cosine of a difference. There's a little bit of setup that actually there's quite a bit of setup that comes first. So I'm going to start with the unit circle. So here it is, unit circle, radius is 1. Lovely. There it is. I'm going to make an angle U. That doesn't really matter where I put it. I don't want to specify where it should be. I want it to be as general as possible. So I'm going to put my angle U down here in quadrant 3 just because that's where I feel like being today. So there's my angle U. It crosses the unit circle at a point right here that I'm going to name A just because it's easier to talk about things when they have names. Since this is the unit circle, the coordinates of point A are the cosine of U and the sine of U, because that's the way the unit circle works. Now I'm going to make another angle V. And again, it doesn't really matter where I put it. I'm just going to stick it over here in quadrant 2. And there's my angle V, starting in standard position over to the terminal side. I'm going to name the point where angle V, I said V, but that surely looks like a U. It's a V. I'm going to name its point B. And again, since we're on the unit circle, it has coordinates, cosine of its angle, which is V, and the sine of its angle. And some other things that we're going to make note of here. In between those two segments that I just drew, that angle, we could call U minus V. U was I came all the way around to here. V was I only got to where B is. So the space in between there is the angle U minus V. And for the sake of simplicity, I'm going to also name it theta. So U minus V is theta, just to save a little bit of writing and for other ulterior motives, which you'll see in a minute. Now what I want to do is take this angle U minus V and rotate it. It's a circle after all, so I'm going to rotate it around until my point B is on the positive x-axis so that I have an angle in standard position. I'm not going to change the size of the angle. I'm going to rotate both sides together. Here's my unit circle again, and I'm just going to take the whole thing and rotate it around so that this used to be point B. I'm not going to call it B anymore because it's in a different place. I'm going to call it D. Am I going to call it D? Yes. And we know its coordinates. Since this is the unit circle, that point is 1, 0. And since I rotated the entire thing around, A now has a new home up here. And we're going to call that C. I rotated the whole thing as a unit. So the space in between the two sides is still U minus V, or theta, two different names for the same angle there. So I can give point C coordinates, because this is still the unit circle. This is cosine of U minus V and sine of U minus V, which I'm going to call theta because it's shorter. My goal is I want to find an expression for the cosine of U minus V, also known as cosine of theta. How are we going to do that, you may ask? Well, I'm going to make another observation about my two circles with their two angles here. If I draw a segment from A to B, and I draw a segment from C to D. Those two segments are the same length because it's the unit circle, the radius is the same, and the angle is the same. So the distance between the two sides of the angle should be the same. So I'm going to make that observation that the segment AB and the segment CD are the same length. Well, if they're the same length, I could say the distance between them is the same. Remember the distance formula from somewhere in your misty past? Here it is. The distance between 2 points is the square root of. This comes from the Pythagorean theorem. Pythagoras has his hands all over the place here. The difference of the x coordinates squared plus the difference of the y coordinates squared. Well, if I do that for AB and I do that for CD, I should get two distances that are the same since those two segments are the same length. So that's what I'm going to do. The distance from A to B, I'm going to look at the difference of their x coordinates. I have my big giant square root here. So we'll do B first, the x coordinate, cosine V minus cosine U squared plus, and then the difference of the y's, sine V minus sine U squared. So there's the distance from A to B. Now let's look at the distance from C to D. The distance from C to D, so we're going to do the same thing. The difference of the x's, cosine theta minus 1 squared plus sine theta minus 0 squared. If you're thinking we don't really need that minus 0, do we? No, we really don't. And we're going to stop writing it pretty quickly here. And those two distances are the same. They're equal. The next thing I'm going to do is I'm going to square both sides. And the main reason for doing that is I don't want to keep writing this big giant square root all the time. So I'm going to square both sides. There's no problem with doing that. If the distances are equal, then their squares are also equal. So it just makes the writing a little nicer, is all that does. Well, when I square, my square root's going to disappear. My square root's going to disappear. So at the same time, I'm going to go ahead and square out all these lovely terms. So this is algebra. And yes, it's going to get worse before it gets better, but it's going to get better, I promise. First thing squared, cosine squared V minus 2 times the first times the second plus the second thing squared. Oh, and that's the first part. Here goes the second part. First thing squared, so I got sine squared V minus 2 times sine V times sine U. And then the second thing squared, sine squared U. Trying to make sure I stay in the frame here. I'm going to do the same thing for the other distance. There's my equal sign. Here we go. Cosine squared theta minus 2 times cosine theta times 1 plus 1 squared. And then, so yeah, sine theta minus 0 is just sine theta. So when I square it, I get sine squared theta. That's a lot of stuff, but good news. Look what we can do. Here's Pythagoras raising his head again in the best possible way. I got a cosine squared V and I got a plus sine squared V. Pythagorean identity. Cosine squared V plus sine squared V is 1. Guess what else? I got cosine squared U. I got sine squared U. Also 1. And hopefully you're way ahead of me and see this one coming. I got cosine squared theta and sine squared theta. Also 1. Well, that's going to make it better. So I got 1 plus 1 on the left. Oh, well, I know that one. 1 plus 1 is 2. And then I got these other 2 terms that didn't fit in there anywhere. Minus 2, I like alphabetical order, so I'm going to put U first. Doesn't really matter, multiplication's commutative. Equals. Oh, all that's left over here is I got this 1 that came from the cosine squared plus sine squared, plus this other one that was there already. And then I got 2 cosine theta. Well, I have a 2 on the left and a 2 on the right. This is an equation. Let's subtract 2 from both sides. There, done. I also want to divide each of my remaining terms by -2. I don't really need to keep writing those -2s. We can do that. It's an equation. I can divide every term by the same thing. And we're there, actually. Now on the left, I have, after I divide by -2, I have cosine theta, which is the same as cosine of u minus v, because way back here, when we started, we named u minus v theta. So we found it. We were looking for an expression for cosine of u minus v. Here it comes. It's what's on the other side after I divide by -2. Cosine u, cosine v, plus sine u, sine v. And that's our identity for cosine of a difference. For the cosine of a sum, I'm going to notice that u plus v is the same as u minus -v, so that's like the opposite of simplifying right there. But the good news is I already have an identity for the cosine of a difference. It's right here. So this is cosine u cosine -v plus sine u sine -v. But remember from recent history, cosine is an even function. So the cosine of -v is the same as cosine of v. Sine on, whoops, that's plus. Sine, on the other hand, actually, is an odd function. So sine of -v is the same as negative sine v. So actually, it shouldn't have been either of those things. This is minus right here. Sine u, sine v. And that's cosine of a sum, or identity for that. And then, well, where did the sine ones come from? We're going to notice that, move it quite far enough out of the way. We're going to make an observation, and maybe you've already noticed this, that say the sine of pi over 6 is the same as the cosine of pi over 3, and vice versa. Oh, totally can't see that at all. And in fact, this observation is true in general. If I have the sine of something, that's the same as the cosine of its complement, pi over 2 minus that something. Works the other way too. Cosine of something is the sine of pi over 2 minus that something. And we're going to use that fact in a moment here. I would like to come up with some kind of expression for the sine of a sum of 2 angles. But all I have to go on is the cosine one that I just found. and this identity. So this is going to be the same as the cosine of pi over 2 minus that angle. Well, I want to distribute that negative through there, so I got pi over 2 minus alpha minus beta, and then I'm going to regroup. So I can say this is the same as cosine of pi over 2 minus alpha minus beta. And if you need a second to look through there and convince yourself that those are really, that's really the same as the line above, it really is, if you think about it for a minute. Well, okay, I have an identity for the cosine of a difference of two angles. It goes like this: cosine of the first, cosine of the second. That's a difference, so I'm going to put plus in between. Sine of the first, sine of the second. But cosine of pi over 2 minus alpha, that's the same thing as sine of alpha. And sine of pi over 2 minus alpha, that's the same as cosine alpha. And there's my identity for sine of a sum. For the sine of a difference, that's going to look like a whole lot like when we went from the cosine of a difference to the cosine of the sum. I'm going to say sine of alpha minus beta is the same thing as sine of alpha plus negative beta. And we'll use our identity for sine of a sum that we just came up with. This is sine alpha cosine negative beta plus cosine alpha sine negative beta, and we'll apply those even and odd ideas again. Cosine of negative beta, cosine is even, so the cosine of negative beta is the same as cosine beta. Sine is odd, so the sine of negative beta is the same as negative sine of beta. And there's the version for sine of a difference. And that is where the sum and difference identities come from.